We're going to start with a little bit of a review of work and energy. These topics were largely covered in mechanics. I hope that you remember something, but there's a specific approach that we're going to take here to think about potential energy of electrostatic systems, of charge systems. So I'm going to try to talk you through a little bit of a review. So first, let's remember something about the conservation of energy. Energy is conserved in a system if it is isolated and non-dissipative. What that means, isolated, is that we don't actually have any sort of outside force. So for instance, if I imagine a ball falling due to gravity, the energy is conserved as long as you consider the kinetic energy and the potential energy due to gravity. But if I grab the ball and I start lifting it up, it looks like energy isn't conserved because I'm actually doing work on the ball. So this is true if work outside, from an outside force is equal to 0. We call that isolated. Non-dissipative means that we don't have to worry about friction or any sort of drag force that is turning energy into thermal energy. And we don't really have to worry about that in electricity and magnetism at all. So the statement that our mechanical energy, the change is equal to 0, comes from non-dissipative and isolated. And then we can say that that means that my change in kinetic energy plus my change in potential energy is equal to 0. Another way of writing that is your initial kinetic energy plus your initial potential energy equals final kinetic energy plus final potential energy. One note, we're using the subscript mechanical here since E is also being used for electric fields. So when you're talking about energy, please make it really clear what is energy and what is electric field, and using the subscript M or mech is one way to do that. So then how can we think about potential energy? Now in some situations you're just going to know the equation that defines potential energy, but how can we figure out what potential energy is if we don't already know the equation? Well, one way to think about it is that our change in potential energy is going to be minus, note this minus, the work done by the interaction from an initial state to a final state. So why are we saying interaction here? Well, potential energy is always an energy due to the system. So kinetic energy is energy due to motion. Potential energy is literally due to the configuration of the system itself. So this work here would be due to the system having an interaction, not necessarily due to an outside force. So what this means we'll actually talk about in two contexts in this video and another one. So this will become a little more clear. Now, what is work? Again, a little bit of a review is necessary, and there's two different ways to think about it. One is to assume that we have a constant force, and obviously you can't assume this for all things, but if you do have a constant force, then you get to take the dot product of that force with the displacement. Remember that both of these are vectors, so we have a dot product, but you can also just do the dot product as the magnitude of each of these vectors times the angle between them. If you do not have a constant force, and in mechanics we normally did have a constant force, so we got to use this, but if it's not constant, we actually need to do this integral. And in this case, we're turning our displacement vector into basically an integral over one direction, where we assume that our force at least has a constant angle. So this is pretty complicated if we actually have a changing angle with respect to our path. So choose a path that has a constant angle with respect to your force, and then you just do the integral. So these are a little bit of a review. Let's try to look at a situation we can apply this to. And that's going to be gravity. Now, you know a lot about gravity already, and you probably off the top of your head remember the equation for potential energy from gravity. But let's actually think through how to use those equations to calculate it, since this is going to be our analogy for a uniform field. Now, one thing that the book has brought up, but I haven't stressed so far, is that we can actually think about a gravitational field. And the gravitational field near the Earth is going to be constant. And so this is really lovely in that just as a constant gravitational field times our mass will actually give us the force, that's just like taking a constant electric field and multiplying it by a charge to get a force. So this is a really nice analogy. So when we think about the interaction, that work due to the interaction, that would be some sort of particle with a mass moving downwards due to the force of gravity. And in that case, you actually have an angle of 0 between these two. And we can then use that work done due to this interaction between the gravitational field due to the Earth and our particle to get potential energy. So in that case, and excuse the line breaking here, that work done is again going to be that force due to gravity times our displacement and the angle between them. Again, it's 0 because they're both down. So that displacement is just going to be y final minus y initial. And I've used the magnitude here because in this case we just have a magnitude. So this can't be a negative number because we've taken the direction into account with the cosine of the angle here. So that's going to give us the y initial minus y final, because again we want this magnitude, we don't want this to be negative. But then when we go to actually talk about our gravitational potential energy, and sorry, this should have been a g, that our change is final minus initial. And again, this here is the definition to put that minus sign here. So we just switch the sign, right? So we get a minus sign here, we get a plus sign there. So that's the same thing as final minus initial. So that was our change. And remember that our change is always equal to final minus initial. So we can just say that our gravitational potential energy for some height y is equal to mgy, or mgh, which we usually used, plus some initial potential energy. Now, we are frequently going to set that equal to 0, right? I can choose my potential energy to be equal to 0 wherever I want. But one thing to be careful about is that our starting point is not necessarily going to have 0 potential energy. So it's really helpful to remember that we're basically doing an integral, and then this is just that integration constant. Because when we go and talk about some more complicated electric fields and the potential from that, this value itself might not be 0. So please be careful about that. And if you feel like you need more of a review on any of these, you can go back and look at the Physics 202 videos where explorations of work and conservation of energy and potential are done in more detail.